Hi everyone, welcome back to Calculus 2 by Example. In this video, we're going to be looking at a couple sets of slides on alternating series. So alternating series are series that are sometimes negative and sometimes positive. And on the first slide, we're going to look at using the alternating series test to determine whether or not a series converges. And in the second slide, we're going to be looking at using the error bounding theorem in order to approximate what a series adds up to or what it converges to. Okay. For the alternating series test, the first thing we want to do is rewrite our series as -1 to a power times another term. Okay, so here this series can be written as -1 to the I times the quantity 1 over I. So we want to focus now on the piece that is not alternating. Okay, so I'm going to focus on the 1 over I or 1 over n. The letter really isn't that important. And so the first thing I want to observe is that for all n, this is positive. That's actually step 1 of the alternating series test. Once you split the summation into the alternating piece and the sort of non-alternating piece, the non-alternating piece you want to be positive. Okay. Next, I make the observation that as n goes to as n increases, u sub n is always greater than u sub n plus 1. So what that means is 1 over n, like 1 over 2, is greater than 1 over n plus 1, say 1 over 3. So a half is bigger than a third, and a third would be bigger than a quarter, and a quarter would be bigger than a fifth, and so on. Okay, so the piece that isn't alternating is positive. That's condition 1 for the alternating series test. The terms are decreasing. Okay, as we move from one term to the next term, things are getting smaller. And as we take the limit as n goes to infinity of those terms, I get 0. So not only are they getting smaller, but the limit is going to be 0. Okay. These are the three conditions for the alternating series test. The non-alternating piece is positive, the terms get smaller step by step, and then when you take the limit as n goes to infinity, you get 0. Okay. So this series, this summation, is going to converge because it passes the 1, 2, 3 conditions for the alternating series test. Okay, so this summation converges, which means it adds up to something, but that doesn't tell us what it adds up to. Okay, so how are we going to determine that? Well, what we're going to do is we're going to approximate that using the error bounding theorem for alternating series. And what that theorem tells us is that if we compare the entire summation S to the partial sum S sub n, the difference between those is less than the next term in the series u sub n plus 1. So S is the entire series, S sub n is the partial sum that goes to the nth term, and the difference between those will be less than the n plus first term. Okay. So I need to know what the n plus first term, so I need the partial sum. So let's say I take the partial sum S sub 10, so that's the summation I equals 1 to 10, and that equals -0.6456 something, something, something. And then I need the n plus first term, so in this case that'll be u sub 11, because it's the term that comes after 10. 11 is the next number after 10. And u sub 11 is 1 over 11, because remember, the u sub n's are just the non-alternating piece. And 1/11 is about 0.091. So it's a little less than 1/10. And so what the error bounding theorem for alternating series tells us is that the summation of S, the sum of S, is somewhere between -0.6456 minus 1/11, which is about -0.737, and less than -0.6456 plus 1/11, which is around negative 0.555. Okay, so this adds up to something between negative 0.73 and negative 0.55. So probably somewhere around negative 0.6. Okay. So that's how we use the error approximating theorem to get an approximation of the summation of a convergent alternating series. All right, so in this video we looked at alternating series, which is different than what we did for the convergence tests, where our series always had positive terms. And so this concludes our brief look at sequences in series, or examples of problems involving sequences in series. In the next set of videos, we're going to look at exercises involving power series, which are kind of like infinite polynomials. That's not a precise definition, but it will give us a nice picture in our head. And so I will see you later for those videos.